Cool. I think we're good now. Um, yeah. So welcome back. Again, talking about more regression stuff today, finishing out. I know last time was very sort of pie in the sky, like conceptual stuff. Today we'll get down to more like in practice, how do we run these regressions? And like I said, pretty much the last half is going to be a review of biostat stuff. So, um, but it'll be much needed, right? Like it's like the most important thing. And I still have to kind of go back over how, a t-test is just a special case of regression, and ANOVA is just a special case of regression, right? They're all kind of subsumed by this idea of regression. And hopefully that'll be clear. If you've already poked around with the lab, the goal of the lab is to like get you to make that connection, but it might make more sense after today. Cool. Sweet. So we'll be talking, first of all, just, finishing up talking about regression. Then we're going to talk about what if we violated our assumptions, right? Because remember, think back to biostats, right? You've got certain assumptions you're making when you do a regression, right? So like the trend should be linear, right? It shouldn't be all curvy or anything. There should be an equal variance as you go up the line, right? So the points shouldn't flare out or anything like that, right? So hopefully that's ringing a bell. If you violated these assumptions, though, you can't really trust your model, right? Your inferential tests you do on like, oh, is this slope significant? They're questionable now, right? What can we do when we violated assumptions? So kind of like randomization tests and things like that, you can actually use robust standard errors. So there are these standard error adjustments that make your tests robust to violations of equal variance. So think back to like biostats, right? Remember the independent samples t-test? And y'all did like, you're comparing these two groups, but what if they don't have equal variances, right? What if you've rejected the null hypothesis that they come from populations with unequal or equal variances, right? So you can't make that assumption. You just have to use the Welch's test, right? Which uses an adjusted standard error. And it's usually a bigger standard error, right? Because more error, you're taking a penalty because you can't meet that assumption. It's the very same idea. We just apply it to regression. Then we'll also talk about more bootstrapping, like how do you do bootstrapping in regression? It's really cool. It's the same idea. Then we'll talk about biostats review stuff, so how to interpret regression output. And then I have an example at the very end that kind of maps onto the one on the homework, and I also walk through those interpretations. You might also check out your old lab handouts and stuff, just in case. I know you're probably rusty on this stuff, but it's like the most important thing. It's the most important topic in biostats because everybody uses it, right? Regression models are everywhere, no matter what kind of research you go into. Even if you don't go into research, if you go into like industry, trying to predict, some response that's numeric from a bunch of variables, that's a regression, right? Really important stuff. Cool. And then next week we'll be sort of segueing into, well, what happens if we don't have numeric outcome data? Like what if we just have binary outcome data? What if we want to predict, whether a patient is going to survive or not based on their, biopsy results or whatever it is, right? That's logistic regression when you have a binary outcome variable. So we'll spend a lot of time talking about that. It's also very, very useful, and odds ratios are going to pop back up again. Yeah, sweet. Oh yeah, I got some new tweets. I thought this was super cool. I don't know who this is, but look at these. Oh my God, our session aborted. Object of type closure is not subsettable. You've probably gotten these errors at least once so far in this course, right? This person is just sort of taking lemons and making lemonade, as it were. And then this is a pretty good, so you've probably come to feel this way too, right? I'm starting to think that 90% of programming is getting software installed correctly. Especially if you've been fussing with it on your own computer, right? Hopefully you got it set up at the beginning of the semester when we walk through it, right? But if you put it off, you're probably grappling with it now, and it can be a pain. The Python stuff and the Project 3 stuff, it's definitely 90% of the battle. It's just getting that stuff working. And hopefully the servers will cooperate and everything will be hunky-dory, but we'll just have to see how that goes. Cool. And feel free, like at any point, holler at me if you have questions in the chat, and I'll try to keep my eye on that. as I go. I know I tend to like just start blathering and not shut up. So definitely like cut me off if things are weird or you have a question. Oh, so I have a thread this week. You've probably seen this because it was going around a lot, but it's definitely the best like Zoom bomb I've encountered. Uh, so I'll just play it, right? I posted it in the discussion board too. I don't know if the volume's not going to work, but the volume's pretty funny too. But uh, so yeah, yeah, dealing with this new normal is you know, takes some adjusting. So I just think that's so rich. It's just her expression. This is the equal parts like just you know cracking up and totally embarrassed. Anyway, I don't know if y'all can see that or not, but check it out if you haven't. Uh, cool. So from last time, right? I just wanted to quickly review because I know we kind of ran through it rather fast. This idea of controlling for something, right? It's fundamental. Like you want to be able to do this. Like imagine you're a researcher and you want to say like, you know, there are these differences in outcomes in like educational attainment for different subgroups, but if we can control for their socioeconomic status, we don't see those differences anymore, right? In order to be able to like ask or answer a question like that, you have to be able to control for it. That's effectively saying, if we control for socioeconomic status, do we still see differences in outcome by certain subgroups? Things like that, right? Uh, so the example I use in biostats to kind of motivate this is like, you know, if you've got, imagine there's a strong relationship between the number of ice cream cones sold in a given day and the number of swimming pool injuries, right? So like someone makes the claim that, oh, the ice cream industry is causing kids to get hurt in swimming pools, right? Because these variables, they're very strongly correlated. Um, but you might think that's odd, right? What's the causal connection between ice cream sales and swimming pool injuries? Uh, and there really is none, right? Unless you drop an ice cream cone on the ground and some kid slips on it, right? Then I mean, there's no, or kids maybe they eat too much ice cream and they sink or something. I don't know, right? But there's not a good way to connect those dots that makes a lot of sense. What's going on there, right? You might remember we talked a lot in biostats about like confounding variables. So if you control for a confounding variable, basically you can say, hey, well, maybe what's going on is like temperature. Ice cream cone sales go up when temperature goes up, and swimming pool injuries go up when temperature goes up just because there's more kids swimming, right? It's warm, people want to swim more the hotter it gets. Um, so the way you would ask the question is like, if we control for uh, temperature, right, then do we still see that positive association between ice cream sales and swimming pool deaths? So imagine you looked at the only days where the temperature was over 100 degrees. So you only looked at like really hot days. And of those days, you look at the relationship between the number of ice creams sold on that day and the number of swimming pool deaths there were on that day. Chances are there's not going to be a relationship anymore, right? If the relationship is being driven exclusively by temperature, right, then you'd expect a flat line if you just, you know, looked at the relationship within that subgroup of very hot days, right? So we can control for temperature and see if there's still a relationship between ice cream sales and swimming pool injuries. Um, and you couldn't really do that. I mean, there are ways to go about it, but regression is such a great framework for that because it controls automatically. Like when we fit this model right here, we're predicting blood pressure from someone's BMI and their blood glucose, right? So we can say, hey, what's the effect of BMI on blood pressure, controlling for blood glucose? And conversely, what's the effect of glucose on blood pressure, controlling for someone's BMI? So it's simultaneously, all the variables in the model are controlling for all the other variables when you look at their effect on the response. So right, so the null hypothesis, you'll always state your null and alternative this way when you're doing these kinds of regressions, right? Because it's really when you test this coefficient to see if it's significant, right? This coefficient estimate, it was fit in this model where glucose is and where blood pressure is, right? So all three, like it's fit in the context of glucose. So controlling for glucose, does BMI explain a significant amount of variation in blood pressure, right? Is the slope equal to 0 controlling for glucose? Because glucose is in the model. If you wanted to test this one, you just say controlling for BMI, glucose does not explain variation in blood pressure, right? That's your null hypothesis. You'd like to reject that. And we saw last time, right? If you run this model in R, you can just say, hey, give me a linear model. We're just doing a regression, right? Predict blood pressure from BMI and glucose. No interaction, just the main effects. And it's going to be like, well, hey, where do I find that data? You just tell it where the data set is. And then you call summary on that fit object. And it gives you this nice little output, right? It gives you the estimate. So little b0, little b1, little b2. It gives you the standard error for each of those statistics. And then it gives you a t-statistic, which is just the estimate divided by the standard error. And then you get your p-values, right? But it's interesting, right? So looking at these two hypotheses, these two null hypotheses, we're testing BMI in this first one, right? Controlling for glucose, BMI does not explain variation in blood pressure. Well, the p-value is way less than 0.05 here, right? So you can reject that null hypothesis. You can say, yeah, the BMI does have an effect on blood pressure even after we've taken glucose into account. Even if you look at people who have the same blood glucose, right? Even if you zoom in on people with high blood glucose, you still see a positive relationship between BMI and blood pressure. If you look at people with low blood glucose, you still see that relationship, right? Holding it constant, there's still a relationship between BMI and blood pressure. However, when you take BMI into account, there's no longer a positive relationship between glucose and blood pressure, right? You can't reject that null hypothesis that the slope for glucose on blood pressure is equal to 0, controlling for BMI. Cool, so that's how you'd interpret that. But again, it doesn't really make sense, at least it didn't to me until I saw like a picture of it. I really wanted to see what this was about. So again, you can imagine there's 3 dimensions here, right? BMI, glucose, and blood pressure. The relationship between BMI and blood pressure is positive, right? And the relationship between glucose, this axis, and blood pressure, the vertical axis, is positive. But which one's steeper, right? So this is the cloud of all your data points. If you plot all I think there's 155 points in 3 dimensions, right? In the blood pressure, BMI, glucose space, you get this cloud of points. And when you run this regression, it's finding the best fitting plane through those points, right? It's a perfectly flat plane, so it has to wiggle around until it minimizes those residuals, right? Those yellow lines. And so it has to make compromises. This is the best sort of angle you can get on that plane to minimize those residuals. So then you can look at it one side at a time and be like, well, wow, of this plane, when I look at this plane, this edge of it, the BMI relationship with blood pressure edge is still very steep, but the glucose relationship with blood pressure edge is pretty flat, right? And that corresponds to these right here. That's the slope for BMI on blood pressure, and that's the slope for glucose on blood pressure, right? BMI is much steeper, and it's significant, right? Significantly positive. We think that there's, even after you take into account glucose, there's still a relationship between BMI and blood pressure in the population. And I know I talked about this last time, but it's important, right? It's a really important idea, but it's sort of weird to think about, right? And again, like most people who, even plenty of researchers who do this kind of modeling don't really have this geometric understanding of what's going on there. But it really, I mean, and maybe geometric stuff isn't your bag. You don't like to see the plots, but I personally, it didn't click for me until it was like, oh, okay, I get it. I can see both sides, right? And things do get weirder with like interactions and stuff like that. With interactions, you're not dealing with a flat plane anymore. You're dealing with like a surface that's potentially bendy. So visualizing those becomes, almost like you just sort of, at that point, you sort of know what you're doing and you don't have to worry about it. Cool. So that's the equation for this plane, right? If you plot in 3 dimensions, it's just your intercept, your slope for BMI, your slope for glucose. Cool. We also talked about, oh, this is the view from the sides, right? You can look in the front of the box and see that relationship, the BMI blood pressure relationship, and then the glucose blood pressure relationship. If anybody's having trouble finding the data, you might grab the worksheet from last time. Let me see here. Let me just read it off my site. So here, let me actually grab it for you. Just to I'll paste the code in the chat. How about that? Oh, but no, that's crap because you can't. I don't think you can copy text out of the chat, which is a really weird feature. But that's the code to get the stuff out of the. Really, all you need is to read in. I should have stuck that in at the top of the CSV. I'm sorry, at the top of the worksheet. But I just pasted that code in the chat. It's probably easier if you just go back to worksheet 14 and rerun that code for MedDat. Because I don't think you can select. Can y'all select stuff out of the chat? Like, can you highlight the chat? I remember someone having a problem with that. No, you can't select it? That's annoying. Yeah, that's so annoying. I wish there was a way around that. Just open worksheet 14 too from last time. And just, control F for my name, I guess, and that's the easiest way to find it. And you'll probably want to run all this other crap too, just to clean it up if you haven't. If you're following along last time, it should still be in your environment. I should have put it in the worksheet anyway. Cool. Another way that's kind of helpful to think about controlling for, right, that we talked about at the end of last time, you can literally do it like manually, right? So if you want to look at the effect of blood pressure, the effect of BMI on blood pressure, controlling for glucose, you can literally control for glucose. You can remove the effect of glucose on blood pressure. You can remove the effect of glucose on BMI, take it out entirely. And then you can see, hey, once I've taken that out, what's the relationship between what's left of BMI and what's left of blood pressure, right? As I've removed the effect of glucose from both, right? And that's what residuals are. Like they're the effect of, like they're the unexplained stuff. So if you regress like blood pressure on glucose, that's how much of blood pressure you can explain with glucose, right? So if you save the residuals, that leftover stuff, that's how much you can't explain. So if you save those leftovers, do the same thing for BMI, take glucose out of BMI and save those residuals, then you can look at the relationship between the blood pressure residuals and the BMI residuals and see if there's still a positive relationship. If there is, then yeah, once you've accounted for glucose, BMI still has a positive impact on blood pressure, right? If there's no association anymore, then you can't. So you can rerun this, right? So just fit a model predicting blood pressure from glucose, save the residuals, save what's left, right? What you can't predict with glucose. That's what's left in blood pressure, the variability in blood pressure that's left over once you've accounted for glucose. So we've removed glucose. Do the same thing for BMI. Take the part of BMI that overlaps with glucose, get rid of it, save what's left over, save the residuals. And then we can see, hey, is there still a relationship? Can we still predict blood pressure from BMI once we've taken out the effect of glucose? And you see, you get the same value from before, right? 0.6205, right? 0.6205. It's the same value we got when we just ran the regular old regression, right? It's just kind of cool to see, oh, okay, like I can get this number if I do it myself, right? I like to be able to do that personally. Cool. Neat. So give it a stab if you want, right? So try to modify that to see if there's an effect of glucose controlling for BMI, right? So you could do like, you could do just take take glucose, remove the part you can explain with BMI, take blood pressure, remove the part you can explain with BMI, and then see if the leftover variability in glucose is associated with the leftover variability in blood pressure, right? That's all there is to it. And again, no one does this in practice. You wouldn't do this in practice. This is just to show you like how to think about it, right? Because it's, again, like I never saw this. This was something I kind of had to figure out for myself. But once it started clicking, it was like, oh yeah, that's it. That's all there is to it. And you can see the effect of glucose once you've taken out BMI on blood pressure, is 4.75 times 10 to the negative 2. So 0.004, right? And that's what you see. 0.04, just moving it back twice, 0.0475. It's 0.0475, right? Same value. Don't know why it goes to scientific notation, but it's kind of annoying, but there it is. Or you could just call summary on this thing if you wanted and see like the full output, and you'd see that it's not significant and stuff like that. Cool. Just ways to think about controlling. It's all sort of just for your conceptual understanding, which to me is like the most important thing. Like any sort of trained, primate can click run on a model and, look at a p-value, but like actually understanding what's going on under the hood is like, like that's when you really are starting to get it. Cool. Sweet. So the great thing about these linear regressions is that you can use both numeric and categorical explanatory variables simultaneously, right? So in this previous example, we were just looking at glucose and BMI and how they impact blood pressure, right? And they're both numeric, but you can include categorical variables too. And as you probably remember from biostats, right? Like categorical variables get dummy coded under the hood. So, they'll get coded as, if you have, like yes, no, or something, it'll be coded as ones and zeros, right? So here's a simple example. Imagine you just want to predict blood pressure from someone's diabetic status. So whether or not they're a diabetic. And that's it. And that's just one categorical variable, right? So we've got blood pressure, which is numeric, diabetic, which is just one categorical variable, right? In R, it gets automatically dummy coded when you run the regression. But I just kind of want to show you what that looks like. So always there's got to be a zero, right? So there's always going to be a zero value and there's always going to be a one value. And it's kind of arbitrary which is which, but keep track of which is which because zero is always the reference group. So for example, maybe you want to code it this way. This is what R would do. Because R by default makes the reference group the first alphabetically. And since no comes before yes in the alphabet, no gets a zero, yes gets a one, right? So you show it this categorical data and R thinks of it as this vector of numbers, right? Or this column of numbers. Cool. So again, you don't need to do that manually. You can if you want, but you don't need to do it manually. R does it for you, right? And you can see right here, run this regression, predict blood pressure from diabetic status, give it the data set, and call summary on it. And here's your output, right? So this is interesting. So think back, like, what sort of a test are we doing? Oh, sorry, let's see. Oh, let me go back. Yeah, exactly. So, or the residual blood pressure is the stuff that's left over. I'm just checking out the chat. The residual blood pressure is the stuff that's left over once you, so if we go back, I should have looked at that earlier. It's different in both scenarios, right? In this scenario, the residual blood pressure is what's left over once we've taken out BMI, right? So that's, once you remove BMI, how much of the variability in blood pressure is left? Like once you remove what you can explain with BMI, how much is left over? That's the residual blood pressure once you take out BMI. Again, don't sweat this if it's not doing it for you. It's just a way to, I mean, and it is sort of a complicated way to think about it. Don't get me wrong. But it's like, as soon as it starts to make sense, it can really sort of be an enlightening way of approaching controlling. But it does, like, some people don't like this explanation, so it's just the way it goes. But we're just taking out the effect of BMI on blood pressure and the effect of BMI on glucose. So once we remove BMI from the equation totally, right, is there still a relationship between what's left in blood pressure without BMI and what's left in glucose without BMI? And in this case, there's not. It's not a significant relationship. I'm not sure if I even put this in the worksheet. This is totally just a conceptual thing. It might be in, I think it's in last week's. Is it in last week's? I mean, not last week's, Mondays. It's probably in Mondays, because this is all review from last time. I mean, like we talked about this last time. I'm not sure if I have it in here though. Let's see. Yeah, I'm not even sure if it's really just a way of thinking about it, right? So there's not a lot of code to really look at. You're just regressing one thing on another, saving the residuals. Totally conceptual. I won't ask you to do that or anything. I just want you to think about it. Cool. Okay, so back to the regularly scheduled stuff here. So, right, regressing blood pressure, which is numeric, on a single categorical variable, right? So we're looking at the relationship between a numeric response variable and a categorical explanatory variable, right? So if you think back to biostats, that's one of the tests we did pretty early on, right? You're looking at whether one group differs from another group, diabetics, non-diabetics, in terms of blood pressure, right? That's just a t-test, right? Independent samples t-test. You've got two different groups. You've got a response variable. But here we're running a regression. So what is this output, right? What's going on here? We've got an intercept. We've got a slope, but it really doesn't make sense because diabetic's not numeric, right? For every 1 unit increase in diabetic status, like that doesn't make any sense, right? Diabetics, yes or no. So how do we interpret these coefficients? We can see it's significant, right? Happy stars going on for our diabetic effect. But how do we interpret that? So take a look at this. Let's just run a t-test on the very same data. So use your good old t-dot test. You can give it the data set. We want to do blood pressure by diabetic status. We'll assume the assumption of equal variances is met, right? So just set that equal to true. And hey, take a look. P-value, 0.02282, 0.0228, right? Same p-value. T-statistic, so 2.299, 2.23, right? It's the same if you round it. Don't worry about the sign. The sign doesn't matter. It's just like whether you subtracted diabetic yes from diabetic no or vice versa, right? Sign doesn't matter. Same t-statistics, same p-value. Take a look at this. Mean in group no, 69.626, right? So of the people who aren't diabetic, that's their mean blood pressure. You see that anywhere in the output? It's your intercept. Strange, right? So that's your reference group. The reference group is the non-diabetics. They get coded 0, they're your reference group. They're the one that's not in the output. Diabetic yes is here, diabetic no is nowhere to be seen, so they're your reference group. So when you're non-diabetic, this is the average blood pressure for non-diabetics. 4.302. What do you think this is? Take a minute and think about it. And especially compare these two means, 69.626, and then for the yes diabetics, 73.929, right? Let me hop on a server. Is a server? No, where's the server at? Let me actually, sorry, my head is in the way. If I can just head juke, let's do that. Yeah, word, cool. So y'all are right. This should seem kind of familiar. It's the difference between those two means. Maybe I don't need to go through the, right? If you take 73.93 and you subtract 69.63, you end up with like 4.3, right? It's the mean difference, right? So you can take the mean of the reference group, 69.626, and add this mean difference. If you do that, if you take 69.626 plus 4.3, then you end up getting 73.92, right? You end up getting the mean for the yes group, right? So this is just the mean difference. It's testing the mean difference. And think about a t-statistic. A t-statistic says, hey, like what's in the numerator? Mean for group 1, so mean blood pressure for group 1 minus mean blood pressure for group 2, right? So mean for diabetic yes minus mean for diabetic no. So this is the numerator of your t-statistic. What's the denominator of a t-statistic? It's just a standard error, right? And this is your standard error. If you divide this, the difference in means, by the standard error, right? The signal divided by the noise gets you this t-statistic, so 2.3. 2.3 is a pretty big t-statistic. You know, I mean, it's reasonably sized, but with 153 degrees of freedom, that's going to be like the critical value here. You could find it if you want, but it's definitely significant. We're out past that 5% cutoff, right? So this is a significant t-statistic. That's all it's doing is a t-test, just with a regression. And you can visualize this, right? You can actually plot, this is the mean for diabetics, right? And it's going to be 74 roughly. And here's the mean for non-diabetics, right? And that difference in means is constant, right? All the way across, because we're not looking at it as a function of any other variable. I know I have an x-axis going on here, but just ignore it, right? The main thing is you're looking at the difference between those two lines. The difference between those two lines is just 4.3, right? Basically the difference between 70 and 74. So it's about, 4. And that difference is significant because we have a big sample, right? So cool, so it's weird, right? You can do a regression on a categorical variable, and if it's got 2 levels, it's a t-test. That's all it's doing. And this is your regression equation, right? So you can plug in 0 to get the predicted blood pressure for non-diabetics. So if you plug in 0 there, 4.3 times 0, that term drops out, and you're just left with the mean, right? Because that's your best guess for non-diabetics for their blood pressure, right? Is the mean of their blood pressure. You know nothing else about it, so your best guess is going to be the mean. So if you know somebody's a non-diabetic, your best guess for their blood pressure is this red line because it's the average and you don't know anything else. If you know that they are a diabetic, then you're going to guess this, right? Because that's the average for non-diabetics, and that's the best you can do, right? Cool. You might be thinking this is weird and I'm sort of like doing something wrong, or like this isn't allowed. But check this out, right? Like you may think R is just doing something magical behind the scenes, but we can actually use this estimator that we derived last time, right? So we can take the sum of the squares of our predictors and then take the sum of the squares of our predictors times the response variable and divide that by the sum of the squares of the predictors themselves, right? And this thing is going to give you those estimated coefficients, right? So we can take, I'm going to make a matrix that has a bunch of 1s, and then the dummy coded for yes, diabetic, it'll be a 1, no diabetic, it'll be a 0, right? So just to go back, just to sort of show you, where do we dummy code that thing? Yeah, so like 1, 0, 0, 1, 1, 1. I'm just taking this column, 1, 0, 0, 1, 1, 1. That's just like, is person 1 a diabetic? Yes. Is person 2 a diabetic? No, no, yes, yes, right? And here's my response variable. Right, that's just the mean blood pressure. I'm sorry, that's just the blood pressure data. So this is person 1's blood pressure, this is person 2's blood pressure, person 3, right? So if we take the sum of the squares of this matrix, the explanatory variables, and add them up, and we invert it, and then we multiply that by the sum of the squares of x, the explanatory, times the response, hey, 69.626, 4.3, right? Exact same thing. So this is all, this thing is all a regression is doing. That's what it's doing when you run it in R. It's kind of cool to see you can get that by hand with these matrix operations. But again, don't sweat it. I won't ask you to, you might have to run this once for the lab or something, but you won't have to really get nitty gritty with it or manipulate it or do anything like that. Cool. But what if we want to control for something, right? So we can do a t-test, and it's like, sure, we found that diabetics have significantly higher blood pressure than non-diabetics, right? That's what the t-test did. That's what our regression showed us, right? We had the significant p-value. But what if we want to control for BMI? So what if we want to say, like, once we take BMI into account, is there still a significant relationship between diabetics and non-diabetics in terms of their blood pressure, right? Do they still differ? Because maybe what's going on here is BMI is a confounding variable. Maybe like diabetics just happen to be more likely to have a higher or lower BMI, and also blood pressure tends to go up with BMI or something like that, right? And so if you control for it, maybe that was a spurious relationship. Maybe it had everything to do with BMI, but not really diabetic status. So if we can control for that, right, we could just look at people in different groups of BMI and see if there's still an association between diabetic status and blood pressure. That's what controlling for does, right? All we need to do though is run the model, right? You won't ever have to like do it manually. You won't have to look at a plane. You won't have to like take the residuals and do that weird thing. That's just to help your conceptual understanding. That's what happens automatically when you run the regression, right? So basically we want to know whether or not diabetic status, you can say explains significant variation in blood pressure. That's a fine way to say it. Controlling for BMI. So once you take BMI out of the equation, is there still a relationship between diabetic status and blood pressure? And then vice versa, controlling for diabetic status, does BMI have a significant effect on blood pressure, right? So once you've taken diabetic status out of the equation, you can look to see if BMI and blood pressure are still associated. And all we do is we run this model, right? So linear regression, we want to predict blood pressure from a categorical variable, diabetic, and a numeric variable, BMI, right? Summary fit, and we look at the results. And hey, what do you know? So take a minute and look at this. And you can always write out the full equation, right? In fact, I'd kind of encourage it. So what this is saying is we can model blood pressure as 49.63 plus 1.23 times whether or not someone's a diabetic plus 0.64 times their BMI, right? So cool, but take a look at these, I mean, just to sort of zoom out a minute, take a look at the significance, right? So diabetic status, yes, is no longer significantly different from the diabetic status, no, right, the reference group. This is the mean difference now. Remember before it was like 4.3. Now it's only like 1.2. And again, we have to sort of, well, no, we don't have to worry about that here actually. So the difference here is small, right? Like it's a much smaller number. And when you divide it by the standard error, you get a much smaller t statistic, which leads to a much bigger p-value, right? But controlling for diabetic status, right, because it's in the model too, when we look at BMI now, controlling for diabetic status, it still has a significant positive relationship with blood pressure, right? For every 1 unit increase in someone's BMI, their blood pressure is expected to go up by 0.64 millimeters of mercury, controlling for diabetic status. So regardless of whether or not they're diabetic. And you can see this. So here's what's kind of pretty about this. This has a really clear geometric interpretation too. So here's the plain t-test, right? Where we're not taking into account the x-axis at all. Like we're not using the information given in the x-axis. We're just comparing the mean of yes diabetic to the mean of no diabetic. And you can see those lines are far apart, right? Those means are pretty spread out. It's a significant difference. But once you take BMI into account, right? Once you sort of allow these slopes to be a function of BMI, you can see that the difference between those two lines is much, much smaller, right? And it's not significantly different. It's only like 1 point something, right? 1.23. So once you've controlled for BMI, the difference between diabetics and non-diabetics, diabetics still have slightly higher blood pressure on average, right? 1.23, but it's not significant. It could just be due to chance, right? So it's neat, right? All we're doing is taking into account BMI. And when we do that, you could run these two regressions separately, right? This is just the line you would get if you regressed blood pressure on BMI for the diabetics. And this is the one you get if you regress blood pressure on BMI for the non-diabetics, right? Like it's the same slope. We're not allowing the slope to vary. Remember, if slopes are changing, you're dealing with interactions. And our model's not that flexible. We haven't allowed the slope of BMI on blood pressure to be a function of diabetic status. We need to interact those two variables if we wanted to allow different slopes, right? But cool, right? So we controlled for diabetic status and we control for blood pressure, and we can see that there's no longer a significant relationship between diabetics and non-diabetics. So you could say like controlling for BMI, persons with diabetes do not have a significantly higher blood pressure than people without diabetes, right? And you could cite the stats or whatever. Cool. So that's, I mean, effectively all we're doing here is a t-test while we control for something else. And this is a beautiful visualization of it, right? You're just looking at the difference between those two lines. Here it's big, here it's small, right? We control for BMI here, small difference. Don't control for BMI, big difference, right? Cool. I think it's kind of cool. I like to look at plots of things when I can, because a picture's worth 1,000 words, right? Like you can really start to see what this is about when you plot it. And sure, you could do a full-blown write-up, right? You could say controlling for diabetic status, there's a significant effect of BMI on blood pressure, right? You could interpret that 0.64, all right? The slope, both of those slopes are 0.64. They're the same. We haven't let them differ, right? And it's significant. You can cite your stats. However, once we control for BMI, there's no longer a difference between diabetics and non-diabetics, right? Cool. And hey, yeah, sure, you can use the matrix thing if you want. you can totally do it, right? So all we need is a matrix of our predictors, right? So that's just going to be the intercept. It's full of ones. Then we have diabetic yes, no, no, yes, yes, yes. And then here is BMI. So that person's BMI, that person's BMI, person 3's BMI, person 4's BMI, and so on, right? Just get all your predictors in a matrix, put all your response variables, or I'm sorry, your single response variable in a matrix, and then just hit it with our estimator. And sure enough, 49.63, 1.23, and 0.64, right? Same thing as this, 49.63, 1.23, 0.64. Cool. How do we interpret the intercept? Just to kind of, not that you would necessarily. Most people don't fuss with the intercepts, but how might you interpret this? What does this mean? Where is the predicted blood pressure equal to 49.63? You might think back to biostats, but really you can just plug in, like in order for that to happen, this term would have to be 0, and this term would have to be 0, right? So if you want to find the blood pressure, you want to find where it's equal to 49.63, well, that's where diabetic is equal to 0, right? So for non-diabetics, and where BMI is equal to 0. Because if that's equal to 0, that's equal to 0, these terms go away, right? They just turn to zeros, and you're left with 49.63. So the intercept is kind of stupid, right? It's like the intercept is the predicted blood pressure for a non-diabetic who has a 0 BMI, right? That's pretty unrealistic, right? Whereas maybe you want to get the predicted blood pressure of a non-diabetic who has like a 20 BMI or something, right? If you did that, you just do 20 times 0.64, right? And that would be 12.8, right? So then you do 12.8 plus 49.63. That'll give you the predicted blood pressure of someone who has a BMI of 20. You just plug in the values you want, and it spits out the prediction, right? And all the predictions are just points on these lines. That would be plugging in equal 20, right? And for non-diabetics, so it would spit out something like 62, 62-ish maybe. And that's just going to be like 12.8 plus 50, right? Which is essentially 62 and change. So it's all, it's all just a line. Like it's literally just like algebra 1 stuff, like y equals mx plus b stuff. It's just, we're using it to model real relationships based on data we've collected, right? And ask questions about the population, just using these lines. Is that cool? It's interesting, right? It's at once really simple, but also really like, that's a kind of a profound thing that we can model it that way, right? It's pretty cool. But right, so like assumptions, they're everywhere. The assumptions for any kind of linear regression, right? And it's an easy to remember sort of acronym. You can just say line, right? There needs to be a linear relationship between your predictors and the response variable, right? So you can eyeball the scatter plots just to make sure there's no obviously like wiggly business happening. Kirby stuff, I guess I say here. You need independent observations, random samples. So I'm kind of sticking 2 in the same one there, but that's kind of a given, right? They always need to be random samples from the population you're trying to draw conclusions about. So the residuals, they need to be normally distributed. The scatter of the points around your line should be pretty normal, right? So most of the points should be close to your line, fewer and fewer as you taper off, right? And you can get that, you can just save the residuals and plot them. You can also, so like eyeball them, right? So maybe make a histogram or a box plot, or you can do a QQ plot if you want. We'll also talk about 2 tests today that you can do, and all these things are equivalent, right? But they test the null hypothesis that whatever vector you give them comes from a normal distribution. So we'll talk about the KS test. We'll talk about the Shapiro-Wilk test. They're both kind of fun. We won't talk much about them. You can just run them to see if your data departs from normality. And then we need the equal variances assumption, right? So that's the last one. That's the E, so equal variance. You might remember from biostats, this is called homoskedasticity. So homo like same, skedastic It's just a Greek term for like varying. So equal variance. You want things to be homoskedastic, right? You want things to have equal variance. Just like a t-test, right? You assume equal variances in groups. You assume the same thing for a regression. But here we're concerned with the variability of your points as you go up the regression line. So we can look at the residuals and see if they get bigger and bigger and bigger. That would mean they're flaring out, right? Or something like that. You can also do a test. You can do the Broich-Pagan test, which is, it's testing the same thing, right? It's testing if your residuals are significantly flaring, essentially. Or if there's any pattern in your residuals that you can, there shouldn't be, right? It should be random, but if equal variance is violated, then you should be able to, anyway, don't worry about the minutia. It's just a test that like, the null hypothesis is your data is homoskedastic. So if you reject it, you violated that assumption. So basically for all those assumptions tests, when you reject, that's when it sucks, right? Because that's when you violated it. It's sort of the flip of when you do a normal hypothesis test, and like usually if you get a significant p-value, it's like yay, but not with assumptions tests. Cool. If I can, sweet. So what I'm doing here, I'm just showing you, this is the world we are assuming exists when we do a regression. So let's say we're going to do a simple linear regression, right? We're going to regress y on x. We want to know what the slope is, right? We want to test the null hypothesis that the true slope is equal to 0, right? We're assuming that our data comes from a population that looks something like this, right? So this is the population. Like we're going to take a subset of this population as our sample, but we're assuming the population looks like this. So notice, right, as you go up this trend, you can see that the points stay about the same scatter, right? They don't get wide and skinny. They don't look all wiggly. I'm going to start like doing some sort of interpretive dance. And right, there are more points close to the middle of this sort of slanted cloud thing than there are as you go further out, right? And I'm just creating this population, right? So I'm taking a sequence of numbers from -5 to 5, equally spaced, that's 1,000 long, right? So that's my x value. And then my y value, I'm taking like the true intercept is 1, the true slope is 2 times this, plus a little bit of noise, right? So normal noise. So I'm actually adding it to where I know the noise is normal. If I left this off, it would just make a perfectly straight line with an intercept of 1, slope of 2, right? But I'm adding a little bit of normal noise because that's the truth. Like that's what I'm assuming exists. When you assume this is true, when you assume that normality is met, you're assuming that the population looks like this. For each of your x values, or for each of your explanatory variables. So what I mean by that, like if you made little density plots as you went up this thing, that'd be normal, that'd be normal, that'd be normal, right? And you can chop it up however, but it'll be normal however, right? And they all those little normal distributions have about the same standard deviation, right? They're not getting big and small, they're all about the same. So again, this is what we assume the world looks like. Now we get a sample from this and we try to figure out what, whether or not we can reject the null hypothesis that the true slope is flat or something, right? Cool. So this meets all the assumptions, right? Like this is a picture of the assumptions. We're assuming normality of residuals, right? So if you plot your little residuals, how far is each point from the line? There's going to be a bunch of small ones, not a lot of big ones. They're going to be normal when you make a histogram, right? Or roughly normal. And then we're assuming things don't flare out and stuff like that. That's just homoskedasticity. Cool. So here's what's neat. We can take a sample. So I'm just going to take a sample of 25 of these points at random. So this is the population, right? This is the unknowable, wholly, data generating process. I'm just going to take a sample of 25, right? So here's my sample of 25. And this black line is the best fitting line for my sample of 25. The blue line is the same blue line as before. That's the true slope. That's the true regression line, right? Intercept of 1, intercept of 1, slope of 2. That's the true line. I take a sample of 25, my slope's a little different, right? Because it's not perfect. I just have a sample, right? But it's giving me information about this true line, like the true slope, right? And we can then take our actual residuals that we observe in the sample and plot them. And we can assess also whether, the points are flaring out too much or something like that. And again, we know in this example that they're coming from a population that meets all the assumptions. So this is what it would look like potentially if you had a sample of 25 that met all the assumptions. So you could save your residuals and you could plot them, right? And yeah, it looks pretty mound-shaped. It might be a little skewed to the right in this example, but it's not too bad, right? If it looks mound-shaped, you're probably cool. And then you can take the fitted values, right? So the predicted values, and make a residuals versus fitted values plot. So you could just plot the residuals against the fitted values, and it looks pretty random, right? There's not an obvious sort of flaring out or any sort of curvy stuff, right? It looks like kind of like static. We've got this one outlier here that we might investigate, this person showing up here. But that just happened due to chance, right? This is a perfectly valid sample. We just took a random sample of our population, right? It ended up being this sample. Hopefully y'all can see those little gray dots. That's just 25 of all these 1,000 dots, right? But notice what's cool is our estimated slope is pretty close to the actual slope, right? It's a little bit less steep. The black ones are estimated and the blue one's the actual, right? So it's a little less steep, but it's still pretty close, right? And on average, you are gonna be pretty close. So our assumptions look okay. I'm fine with that. So that's just an example with like where we know the population is normal, right? So this is what you'd expect to look like if things are hunky-dory. If we go back to our earlier regression, right? So the one that we ran where we had diabetic status, BMI, predicting blood pressure, right? We can grab those residuals, we could grab those fitted values, and then we could plot those, right? So as we go up the regression line, right? Because the fitted values are just the regression line. It's kind of like just taking the actual plot and, flattening it so you can look at it a little bit better. As you go up that line, I don't think things are flaring too badly, right? It's not super obvious. There's not that many observations out here, right? So there's not a lot of data out here, but it's not too bad. I don't see any obvious pattern here. But again, it sort of sucks to have to eyeball stuff, right? Like eyeballing things is, I always hated that when I was taking intro stats. It was like, give me a test or something. Like I hate looking at this plot and not knowing what good enough means, right? Like, is that good enough? Do I meet the assumption? Like, where's the cutoff? So we're going to talk about tests you can do instead if you're uncomfortable eyeballing things. The more exposure you have to this stuff, you'll get pretty pro at like, yeah, that's fine. Because yeah, that's fine ends up being the answer most of the time. But we can plot our residuals. So this is just testing the assumption of homoskedasticity and linearity, right? We can see, well, we should probably do a scatter plot if we want linearity, but if you don't see any wacky departures from just random noise when you plot the residuals against the fitted values, you're fine. Normality, we can plot those residuals, and hey, that looks pretty mound-shaped, right? That's perfect. And if we do a QQ plot, looking at our sample quantiles versus the theoretical quantiles, it's linear too, right? So that's awesome. These look super normal. But again, you might not like eyeballing that, right? Maybe you want to do a formal test. So I want to introduce you to just two quick tests. If you want to do a test of normality, this is one you can do. So it's very similar to like a QQ plot, actually, but it's showing you the cumulative density of, in this case, it's showing you like the residuals and then the probability of being less than that residual. So like when you get to zero, when you get to a residual of 0, what proportion of all of your residuals are less than 0? It should be about 50%, right? What proportion of your residuals are less than -10? It should be about, in this case, it's like, what's that, like 13% or something? You can get what it is actually in your data set. So the empirical cumulative density, right? So by the time, what proportion of your residuals are less than 30? 100%, right? And you can compare that. So the blue jagged one is our actual data, right? This curve, this nice smooth curve, is what you'd expect if it was normal. Like, so if our residuals were normally distributed, you'd expect this nice dark curved line there, right? So the Kolmogorov-Smirnov test or the KS test, right, is it finds the point of greatest departure between what we observe in that cumulative density function and what we expect for the normal cumulative density function, this little red line right there. And that little distance is the test statistic. And it tests whether that's big enough to suggest that you've got something janky going on in your normality. So you can actually just run this, right? You never have to plot that. I just think it's important to like see what that plot is. But that's all this test is doing. You give it the mean, standard deviation, p-norm, and then you give it the residuals. And you can't reject the null hypothesis because that looks pretty dang normal, right? They're basically overlapping. Like that looks awesome. So this test says you can't reject the null hypothesis that the true distribution of the residuals is normal, right? Another common test is that Shapiro-Wilk test. If you've ever been in my office, you may have seen a cross stitch I've done about a violation of normality. That's the test statistic. The Shapiro-Wilk test has this W statistic. But again, it's the same answer, right? The null hypothesis is that the true distribution is normal. So if you give it your residuals, it gives you a p-value that's very big. You can't reject the null hypothesis. That's good. We've met the assumption, right? So those are just two tests of normality. Again, don't worry too much about them. Eyeballing's fine, but if you want to test, you can use either one of those. It's totally fine. Cool. Oops, that should be on the previous slide. Sorry about that. So model fit, right? So talking about R squared from last time, right? What proportion of the variability in blood pressure can we account for if we know diabetic status and if we know BMI? Like what proportion of the total variability in blood pressure? And remember, like last time we talked about, something flying here, sorry. Last time we talked about like simple linear regression, like, oh, you just take the regression sum of squares out of the total sum of squares, right? Or you can do, 1 minus the error sum of squares out of the total, or like whatever you want to do, right? It's the same thing here. We just have more than one explanatory variable now, right? So cool, so all you need to do is get your sum of squares total, right? So that's just how far is every person's blood pressure from the mean blood pressure squared and added up. So total sum of squares minus the sum of squares error. How far is every person's residual, how far is every person from that fitted line squared and added up, right? So those are just your residuals, those little distances. Square those and add those up, right? That's your sum of squared residuals out of the total. So we can say, hey, sum up blood pressure, the distance from blood pressure to the mean squared, minus the sum of the squared residuals out of the sum of the blood pressure from the mean blood pressure squared, right? So sum of squares total minus sum of squares error over sum of squares total. And that gives you this R squared value, right? 0.187. And that's the same R squared you're getting right here, right? That regression output, when you do summary fit, and then you look at the very bottom, I've just chopped it off to where you can see the bottom. That's your R squared, right? So that's the proportion of the variation in blood pressure you can explain by knowing whether someone's a diabetic and what their BMI is. Close to 20%, right? Just about 19%. It's pretty decent. I mean, it's not great. There's tons of other stuff that affect blood pressure, right? That's a very small portion of, loads of other stuff going on. But those two things get you that's a decent amount. I mean, not decent, like that's by any measure, that's pretty small, but still it's a chunk. You can explain some, right? Cool. And you probably remember from Biostats, this adjusted R squared thing, right? And notice it's a bit lower. Adjusted R squared is just a penalty, kind of like, using a bigger standard error or something like that. And in Biostats, I talk about it like it's a penalty for capitalizing on chance. Because imagine, and I kind of give a thought experiment. Imagine you just take, oh, hey, wait, y'all haven't met Jubes. Jubes, come here, we'll go. Yeah, okay. This is our first cat, Jubes. He doesn't like to be picked up, but he's my good man, Mr. Joby. He's pretty heavy. Oh God, he doesn't love being picked up. He didn't like that. He's probably, yeah, he's a good dude. But that's Jubes. His name is Jubal. We call him Jubes or Big Jehovah or the Jubeless Man, or all kinds of little names that we. Anyway, Cats. You still have to meet, still got another cat. You'll probably see Jubes again. He's a smart cat. He like knows his name and he knows a few words. Pretty smart guy. The one I showed y'all last time, Dinge, she's dumb. I mean, she's the she's the sweetest cat in the world, but she yeah. Oh, there she is. Oh, she's coming. Anyway, we have this pillow shaped like a piece of toast. It's kind of an inside joke from my wife's former job, and Dinge loves it. She sleeps on this pillow shaped like a piece of toast all day long, pretty much. Anyway, so in biostats, right, I talk about the adjusted R squared because you're capitalizing on chance, right? So the thought experiment is imagine you just take a random number generator and spit out, you know, like just a random variable, like completely bogus, just made up numbers. And you regress it, you regress the response variable on it. So you use it as an explanatory variable in a regression model. Just accidentally, it's going to explain some variation, right? There's going to be accidental, like, oh, where the random variable went up, the true, the response variable went up, just due to chance, right? So the more of those you add, the more chance, the more chance creeps in, and you're explaining stuff in the response variable just, it's just bogus. It's like not real information. It's just like there's noise in your variables and you're just capitalizing on chance. So you can keep adding crappy variables to your model that are just made up. And you can end up, if you do a jillion of these, you can get a pretty good R squared just by cramming it full of variables, right? But that's bad news. So the adjusted R squared penalizes you. So it's a good idea to report that one. I'll actually give a brief demo of this if you're curious. Let's just make up 5 completely bogus variables. So I'm going to set the seed here, and I'm going to create a data frame that's got people's actual blood pressure. And then I'm just going to take 155 draws from a random, like a standard normal distribution, right? Mean of 0, standard deviation of 1. Just random numbers, pulled at random, 155 of them 5 times. So I'm creating 5 different variables. You can see here x1 up to x5. And these are just random numbers from a normal distribution. Totally random, not corresponding to anything in the real world, right? If I run a regression of blood pressure on these sort of bogus variables I just pulled out of thin air, right? And I do 155 just because that's the length of the data set, right? That's how many rows are in this data set. So it has to match up. I'm just creating fake data. If you regress blood pressure on that, your R squared actually, so using these made up variables, you can account for about 3% of the variation in blood pressure. But they're made up, right? They're bogus. The adjusted R squared says, 0%, right? So the adjusted R squared is just penalizing you for adding noise variables in the model, or like any kind of just, the more variables you add, the more you're capitalizing on noise, having some accidental association with the response. So the adjusted R squared kind of nips that in the bud, as they say. Cool. So that's all that is. Just a demo of that. I added it like 5 minutes before class started because I thought it was kind of cool to think about. Okay, so fine. So we talked about the hunky-dory sort of world where like everything works and all the assumptions are met. But what do you do if they're not, right? That's kind of the theme of all this, is like, what do you do if assumptions aren't met? Am I actually recording? God, I hope so. Anyway, but I really hope so. Sweet. So what you can do, if your data show heteroskedasticity, right? So if equal variances isn't met, if you see crazy flaring, you can use robust standard errors. You can use a standard error calculation that's robust to that, just like the Welch's t-test, right? If your data is just all kinds of messed up, like just terrible, go ahead and use bootstrap standard errors, right? That's totally fine to do because they're not model based. You simulate them yourself and they're perfectly fine. You don't have to make any assumptions. So for example, let's look at something else now. Let's predict glucose from BMI, and yeah, let's look at it for 2 groups. So let's look at it by diabetic status. So notice, right? Imagine a line going up here. Like the best fitting line through all those points would be, like that. But notice the points are tight towards the bottom, and then they get really spread out as you go up, right? That's bad news. That sort of flaring is not good. And again, eyeballing this stuff sucks, right? Like I always hated eyeballing stuff. There's a nice little test you can do to test whether or not this model is violating that assumption. So it's called the Boyce-Pagan test. And all you need to do, you'll need to install 2 packages if you haven't already. These are 2 packages you're definitely going to need. You'll need them for the project. So go ahead and do install.packages sandwich, and you'll need quotes around it, right? Install.packages sandwich, and then install.packages lm test. You need lm test right now to get that BP test function. So take a minute and do that. I think I give you all that code. Hopefully. If not, just do install.packages. Cool, so then you fit the model, right? Then you say, all right, predict glucose from BMI and diabetic status. That's just this picture right here, right? Then we can do BP test. It's testing the null hypothesis that your data is homoskedastic, doesn't violate the assumption of equal variances, has equal variances, right? Uh-oh, we have to reject that null hypothesis, right? So we can reject the null hypothesis of equal variances. That means we violate our assumption. So bad news, right? And you can kind of see that flaring, you know, it's easier to do the test and be like, okay, yeah, it violates it than it is to eyeball stuff. But so what can you do? Here's where Sandwich comes in. So Sandwich is a cool library that allows you to easily add on heteroskedasticity consistent standard errors or heteroskedasticity robust standard errors. Their standard errors kind of like the standard error in the Welch's t-test, right? That it doesn't matter if it's like your data can be in violation of this assumption, and that's fine. They work just fine. So for example, in your original regression, in your original regression, here's what the coefficients are. So there's your slope, there's your intercept, there's your slope for BMI, and there's the diabetic yes difference, right? And then here's the standard errors, 9.9, 0.03, 4.6. Those standard errors are estimated under the assumption that the null hypothesis is true, right? We're using a t-distribution. Over here, we need to use this function called coef test to get those corrected standard errors. So we say coef test, and you'll need to do library sandwich before you can do that, and library lm test. So do coef test. Once you've loaded those up, fit, and then give it this heteroskedasticity consistent standard errors right here. Just say VCOV HC fit. All you need to do is just run that code. And we're just going to grab the first 2 columns of that, the estimate and the standard error. And notice, estimates are the same, right? Same estimated intercept, same estimated slope for BMI, same diabetic thing, right? Standard errors are bigger, right? Because we're taking a penalty. We didn't meet that assumption. Our standard errors have to be a bit bigger, right? So that'll usually be the case. Sometimes they can be smaller, but it's weird when that happens. A hint for those of you who are tuned in, there is a situation on the homework where they get smaller, and it's weird that they do. But there are reasons why, so you might think about reasons why, but don't worry if that happens. A lot of researchers who know their stuff use these no matter what, because they don't want to fuss with, like, you know, is it homoskedastic or not? It's a good idea just to be conservative in general, right? You don't want to make false positives. You don't want to make type 1 errors, right? You don't want that rate to be any bigger than what you think it is. And there's always so much going on that it's like, it's so hard to control for things. Just be conservative, right? So a lot of people use this just no matter what. If you have a really small sample size, then you're in trouble for normality reasons, right? Or if you violated the assumption of normality. You've probably seen this little GIF, but I love it. Linear regression with bootstrapped standard errors. So, I mean, it works everywhere. It's a beautiful thing. And, you know, it's still, you're making assumptions about linearity and stuff, but like, oh God, sorry, something bad happened. It works like a charm. And it's really not any different than the bootstrapping you've already done, right? So what we can do is take your data set, right? Has your explanatory variables, your response variables, and sample the rows with replacement. So get a new resampling of your data set where you've sort of catch and released each row. You might get row 1 twice, you might not get row 2 at all. Just take a new resample with replacement, right? So we're bootstrapping. Then just refit the model to your bootstrap data, save the estimates, and repeat. And that's all you have to do, right? So resample your data with replacement, run the regression, save your little b0, little b1, etc. Save that, then repeat, like resample, rerun it, save your estimates, right? Your estimates are going to jump around, but that lets you estimate the variability of those estimates, right? That gives you an estimate of the standard error. So if you then take the standard deviation of your little coefficient estimates, you're set. So here's a little way. This is different than I have in the worksheet, I think. The worksheet's an old school, just R, base R kind of way to do it. This is using the dplyr function sample frac. This just takes your data set and takes a random sample of the rows with replacement. All we're going to do is we're going to do that over and over again, 5,000 times. Take a sample with replacement, refit this regression on, and be careful, do it on the actual bootstrap data. So we want to use this resampled data to fit the model on, and then save the coefficients, right? And it'll get saved in this samp.distin thing. You can save them wherever you want. So what you're going to do is you're going to get 5,000 estimated intercepts, 5,000 estimated slopes for BMI, and 5,000 estimated slopes for diabetic, right? If we take this thing and it's on its side, so we're going to transpose it, make it a data frame, and then just compute the standard deviation of all 5,000 for each of the columns, you end up with an estimated intercept standard error of 9.96, estimated BMI standard error of 0.33, and an estimated diabetic standard error of 5.24. So remember that. So 9.96, 0.3, 5.24. If you go back and look, 9.96, so it's bootstrapping, it's a little bit higher. 0.33, it's a little bit higher. 5.34, it's a little bit higher, right? So again, you're kind of taking a penalty. But still, these are beautiful, and you don't make any assumptions at all. It works like a charm. You can use these then to do hypothesis tests or whatever, right? You can get confidence intervals too, right? If you want to know a 95% confidence interval for the slope, right? So for BMI, hey, check this out. So all you do, right? Take your sampling distribution. This is just an easy way to do it, right? So we can just put them all in one column and then do like group it by, just run this, right? And what you end up getting is the lower cutoff for 2.5% and the upper cutoff for 2.5%. So your 95% confidence interval for all of your intercepts, BMI, and diabetic status. Gathers just like pivot longer. Just a little bit less typing. And you can see that like we're 95% sure that the true intercept is in here. We're 95% sure that the true slope is in here. We're 95% sure that the true diabetic status difference between yes and no is in here, right? The null hypothesis is always that it's 0, right? So for BMI, can we reject the null hypothesis here? The slope of BMI is equal to 0, controlling for diabetic status. No, right? You can't reject the null hypothesis. 0 is a value that's in that 95% confidence interval. And if you go way back, we'll probably have to go way back. Where's that model? Right, we saw way back a long time ago. That's just this, oh wait, where'd it go? Oh wait, what are we doing? Oh no, sorry, we're doing one we haven't looked at yet. We're doing the effective, we're doing this one, right? Whether or not BMI is significant once we've controlled for, you could just do summary fit and it'll show you that that slope for BMI is no longer significant for glucose. Because this is testing whether BMI has an effect on glucose, diabetic has an effect on glucose. So once you control for diabetic status, BMI is no longer significant. 0's in that confidence interval, right? That's what you get if you do summary fit. If you ran fit, if you fit this model, right? Cool. Neat. One other way to bootstrap is to bootstrap the residuals. And this is kind of wacky, but some people like to do it better because think about it. When you resample rows or people or whatever, rows of your data set, sometimes you don't get a person at all, right? Sometimes people are left out entirely and you're losing information about people you don't resample, right? And they'll end up in other samples, so that's fine. But here's a weird sort of thing. And when I heard of this, I thought this is a wacky idea, but it's really cool and it works pretty well in practice. So fit your original regression model. Just run your regression. Save your residuals and your fitted values. So save what the predicted values are and save the residuals, the difference between each person's data point and the predicted value. Here's what's weird. Then just take your residuals and resample those with replacement. So effectively, you're mixing people's residuals all around with replacement. So every little person's difference, you're just sort of moving all those little differences around to make some like essentially fake data. You're saying, what would the world look like if I kept my predicted values the same, but I switched up the residuals? So I just scrambled them. If you add the residuals back to the fitted values, you get essentially a brand new data set. It's just made up, right? We've just scrambled the residuals. Then you refit the model to that and get an estimate, and then you repeat. So you just keep re-scrambling the residuals, fitting the model, getting estimates, scramble, fit, get estimates. You do that a bunch. It's strange, but it usually actually ends up being resulting in smaller standard errors. So for example, here's how this might look. Fit this model, save your residuals from it, just grab them, save it as resids or whatever. Save your fitted values or the predicted values from that model, like where on the line do you predict for every person. And then resample your residuals with replacement, make some new bogus data by taking the predicted value plus the resampled residuals, fit the model on the new bogus data, and then compute the coefficients each time. And we're going to save that. We're going to do that 5,000 times, right? And you can do the same thing. You get these estimates, 9.9. Last time it was like 9.96. This is a little bit higher. Last time it was 0.33, so it's a little bit lower. But they'll be about what you get doing it any other way, right? And you don't have to make assumptions. And here's your confidence interval. Notice you still can't reject BMI, so it's the same conclusions. Just another way you can approach that. Yeah, you're going to get slightly different values, right? Because every time, unless you set the seed to be what my seed is set at, you'll get different answers, right? So that's fine. They'll be close, but that's the point, right? You're just taking a random 5,000, and every time you do it, it'll change a little bit, but it'll still be close, right? And the more replications you do, right? If you were to do like 5 million or something, don't do that. It'd probably take about 20 seconds to run, but you know, they'll be more precise. Cool. Yeah, no, that's a great question. Yeah, that's a really great question. Whenever you do any of this bootstrapping or anything like that, you're going to get different answers, right? That's what the set seed stuff is for, just to make sure everyone gets the same answer for like the homework or whatever, or to like try to make that happen. Sometimes it's impossible to get people to have the same answers, but it's fine. Like if you're doing it right, it'll always be close enough. And you can compare all these, right? So here's just the normal theory, the basic standard errors. Here's the robust standard errors, so those are bigger. Here's your bootstrapped with resampling row standard errors. So compare like that column, this, and this. And they're all pretty similar. These will be probably the lowest overall in general, because you're making more assumptions. But they're right around there, so we might not be too bad in terms of violating assumptions. Cool. So this will kind of be what you do in lab, right? So imagine you want to, so like switching gears at this point. So we talked about, the adjusted standard errors. We talked about bootstrapping. What if you just want to find if average blood pressure differs by like age category? And let's say we make some age categories like 0 to 40 is younger, 40 to 60 is middle age, and 60 to 100 is older, right? We just make this factor variable, and there it is, right? So middle, older, young. If you want to do a test like that, you want to see whether blood pressure is different across these 3 age categories. What kind of test is that? We talked about it. 2 lectures ago. It's a, you know, it's a pretty good workhorse of, you got a categorical variable with, you know, you would just do a t-test, but there's 3 groups here, right? Instead, you'd end up doing an ANOVA, right? A univariate ANOVA. If you wanted to do multiple response variables, like if you wanted to see if young, middle, older differed in blood pressure or cholesterol or platelet count or whatever, then you do a MANOVA. But if you just want one at a time, just a regular ANOVA is fine. You can run a MANOVA with a single response variable. It'll just give you a ANOVA output. Cool. So we can take our data, we can group it by the age category. And again, I think the code might have it created without case when, but it'll do the same thing. So the average blood pressure for middle-aged people is like 73. The average blood pressure for older people is like 72. So interesting, there's not a big difference there. But then for young people, it looks about 7 points less, right? So young people have, these are just average blood pressure, but how, like, are they significantly different? That's the question. So you can do an ANOVA, right? So just regress blood pressure. Oh, and here's the interesting thing, right? So you may have noticed when you do an ANOVA, you're saying, hey, linear model, predict my numeric response variable from my categorical explanatory variable, right? And I saved this when I modified the age variable. I saved it as med instead of med-dat, so whatever. Like that's the new data set. And just call ANOVA on this. But look, we're running a regression. We're fitting this model, we're running a regression, and then we're asking for ANOVA output of this regression. And here's the ANOVA output, right? You're between sum of squares, you're within sum of squares, your mean square between, your mean square within, your F statistic, your p-value, right? And yeah, wouldn't you know it, the ANOVA is significant, right? So you know that for at least one group, they have a different mean than the others, right? ANOVA's testing the null hypothesis, all those means are the same in the population. So we can reject that. We know at least one of those means is different. And yeah, eyeballing this, you say, yeah, I bet I know which one it is, right? I bet young is different from the other 2. But you don't know for sure unless you do the post hoc test, right? That's the point. You got to find out which one's different. But here's this model we actually fit. Under the hood, here's what happened. There were 2 dummy variables. There was a dummy variable for middle age, and there was a dummy variable for older. Notice there's no dummy variable for young. Why is that? So maybe young is the reference group, right? And by default, it'll put alphabetically the one that's first as the reference group. So if you just run this in R, it'll put middle as the reference group. But here's the way R thinks about it, right? So here's what's going on. Again, you don't have to do this yourself. R does it for you, but just so you can see, this is the way that R sees it. It says person 1 is a middle-aged person with a blood pressure of 72. Person 2 is an older person with a blood pressure of 66, right? Person 3 is middle-aged, blood pressure of 66. What about person 4? Person 4 is neither middle-aged nor older, right? So 0, 0. That means you're dealing with the reference group. So in this case, by default, the reference group here is young in the way I've set it up here. So that means it's a young person. So when you turn off middle and you turn off older, you automatically know it's a young person, right? Because there are only 3 categories. When 2 of them are turned off, it's got to be the other one, right? And this person has a lower blood pressure, right? Anyway, you don't need this automatically, right? Like this is just what R does for you. And then it just runs the regression on that. There'll always be the number of groups minus 1 dummy variables that R does for you, right? And there'll always be that many coefficients to interpret. Cool. So you can manually change the reference group, right? So like in this category, I mean, in this example, you can run this and we can say, hey, I want to make young the reference group. So you can say re-level and make ref equal to young, and then fit this model, blood pressure by age and summary fit. And hey, take a look, right? This is our output. And think back to that t-test example, right? So remember for the t-test example, the intercept was the mean for the reference group, right? It's the exact same thing here. 65.58, the reference group is young people, right? So young people, this is saying young people on average have a blood pressure of 65.58. If you go back and look, 65.58. So it's rounding it annoyingly to, you know, the 1 decimal place, but that's 65.58. That's young people's average blood pressure, right? What do you think these two estimates are? It's just like the t-test, right? So how much higher are middle-aged people's blood pressure on average than young people? Well, they're 7.3 higher. They're 7.4 roughly, right? Compared to the reference group, they're 7.4 higher. Yeah, that's a significant difference. What about older people compared to the reference group? Well, they're 6.4 higher. Yeah, that's a significant difference, right? So when you do a regression with on a categorical variable with multiple groups, it's just giving you a bunch of t-tests as the output, right? It's like doing all pairwise t-tests. It's the same output. And if you want to compare middle to older, you'd have to switch one of those to be the reference group, right? So maybe set it equal to middle. And now you're comparing young to middle and older to middle, right? And now you can see, yeah, young is different than middle age, but older isn't different than middle age. So it's just like we thought. Young is different from both of the others. The mean for young differs from the mean for middle. The mean for young differs from the mean for older. But older compared to middle doesn't differ, right? Not significant. No happy stars, not less than 0.05, right? Cool. So that's it. That's just, I mean, that's sort of how it's doing. And again, you can, I mean, if you were to like reformat this in terms of sums of squares, you could do the regression stuff, but that's really all it's doing. So it's kind of doing it for you. What if we have two things? We want to look at age categorical. I know we're low on time. But from here on out, this is all like biostats review. So the examples towards the end are really good practice, but feel free to like, if you got to go, no worries at all. But I will walk through them just for, you know, just for completeness. Because interpreting, you will have to do an interpretation of a couple of the coefficients on the homework. And it takes practice. Like you're probably out of the habit. Go back and look at how you did it for your poster, right? Because you probably did it right. You probably put some time and thought into it, right? So just see how you interpreted your coefficients there or something, right? But I have a full example that kind of maps onto the homework question. Cool. So neat. So cool. So predicting blood pressure from age and BMI, right? And here age is categorical. So you can do it just like this, right? This is be like, what's cool about this is you can do a regression. I'm sorry, you can do an ANOVA controlling for BMI if you wanted. You can say, hey, once we take into account BMI, do we still see differences between people's ages, right? Do we still see, you know, the mean blood pressure being different for age groups once we account for their BMI? So if we only look at people with like a high BMI, do we still see young being different from middle and young being different from older or not? That's what we can do with this. That's exactly what this is doing. So control for BMI, it's in the model. BMI, yeah, that's significant, right? So controlling for what age someone is, regardless of what age someone is, there's still a significant impact of BMI. That's what that's telling you, right? The slope is 0.64. But so young is still different from middle, right? So young people still have a blood pressure of 6.3 less than middle-aged people, because again, middle age is the reference group, right? And young people have a value that's significantly lower, right? Older people don't differ from middle-aged people, just like from before, right? So even when you control for BMI, there's still a difference between young people and middle-aged people, which in this case is the reference group, right? You see it's significant. And BMI is significant in general, controlling for age. Regardless of what age you are, there's still a significant effect of BMI, right? So you may have, if you work in a research lab, or if you read, you know, the medical literature, or if you're someone who's, you know, exposed to stats in research, you probably heard of something. You may have heard of something called an ANCOVA. I know it's like alphabet soup, right? There's MANOVA, ANOVA. I even talked to you like about the PERMANOVA stuff. ANCOVA, it's an old school technique. It's fine to do. It's just like, remember when we did the t-test, but we controlled for BMI. We tested diabetic or not. If there's a difference in blood pressure after we control for BMI, right? And those two lines were like this, but then they were like that, right? It's the same idea here, except we're doing it with an ANOVA, right? So that's all an ANCOVA is. It's an ANOVA where you control for some continuous or numeric predictor variable or explanatory variable. So just actually run ANOVA on this thing, right? Because this thing we said predict BMI, predict someone's blood pressure from their BMI and what age group they're in. If you say ANOVA on that same object, it's going to give you the sum of squares. And don't worry about the one for BMI, right? It's saying, yeah, BMI is significant. But this is telling you that, yeah, after you've accounted for their BMI, there's still a difference between people's blood pressure depending on what age they are, right? So it's like an overall test. It's basically saying, are any of these t-tests, young versus middle, young versus older, middle versus older, are any of those three significant after we control for BMI? And it's saying, yeah, right? This is your between sum of squares. This is your within sum of squares. Divide your mean square between by mean square within. You get that F statistic. There's your p-value, right? Very small. So yeah, and you can see, obviously, right? We already know age young is different from age middle controlling for BMI. So there's still a significant difference. And if we were to plot this, I can't remember if I plot this one. No, I don't plot this one. But it would just be 3 lines that have the same slope. 2 of them will be very close together, young and old. I'm sorry, middle and old. And then young would be down below them, right? Significantly further below them. They all have the same slope though, right? They all have the same slope because we haven't fit an interaction yet. Interaction is the only way the slopes can change. We're not letting slope vary as a function of any other variable, right? The slope of BMI can't depend on old, middle, or young. They're gonna have the same estimated slope, which is 0.65. Cool, so don't worry about the ANCOVA. I just wanted you to know what that was in case you've seen it in research. That's all it is. It's an ANOVA controlling for something else. It's kind of handy. Cool, so interactions. Right, again, I'll review. So think back to biostats. An interaction is just testing if the slope, let's say like the slope of BMI on blood pressure, is it steeper for like old people than it is for young people? Or is it less steep? Or are they the same, right? Interactions allow you to test whether the slope or the effect of one variable on another depends on some third variable. And they're really cool, right? They're a lot of fun. So think back to this model. This is the one we were just looking at. Or no, this is the one from way back. BMI is 0.64, diabetic status 1.23, right? So we're looking at the effect of diabetic status and BMI on blood pressure. Cool, and you can run this regression. There's no interaction, right? We're fitting these as 2 separate terms, no interaction. So this is called main effects, right? You're dealing with the main effect of diabetic status, main effect of BMI on blood pressure. And yeah, they're each controlling for the other, but they're not interacting. And this is what we saw before, right? Diabetics no longer significant from non-diabetics in terms of blood pressure after you control for BMI, right? But what if we add the interaction? So what if we add the interaction of diabetic status and BMI? So by adding this term to our model, right? And this is just a, this is just a line, the little b naught, I guess really it's like a 4-dimensional thing, but the little b naught there is, that's your intercept. That's your slope for diabetic. That's little b1, that's little b2, that's little b3, right? This is really cool because what we're doing here is we're allowing BMI to vary depending on whether someone's diabetic or not. So think about it. When you're not diabetic, you plug in a 0 here, right? So this term goes away. So for non-diabetics, the slope is just going to be little b1. So notice, right? This is the slope for non-diabetics, little b1. And again, that's a silly thing because it's when BMI is equal to 0. But this is saying when BMI is equal to 0, like interpreting this slope right here, right? When you plug in 0 here, 0, 0, then you're left with little b1, right? When BMI is equal to 0, non-diabetics have blood pressure that's actually higher than diabetics, right? So this is saying diabetics are 1.6 lower than non-diabetics. That means they have lower blood pressure than non-diabetics. But it's really weird because that's a stupid thing. Like we're making a prediction where BMI is equal to 0. That doesn't make any sense. So don't worry about that right now. We'll talk about that in just a second. What you should notice though, there's no significant interaction here. So this little b3 tells you this is an estimated difference in slopes between diabetics and non-diabetics for the effect of BMI on blood pressure, right? And it's not significant, right? So just eyeball it. The p-value is not significant. So there's no significant difference in the slopes. We know those have the same slope. We can't reject the null hypothesis that diabetics and non-diabetics have a different, the BMI has a different effect on blood pressure for both of those groups. We can't reject that, right? BMI still has the same, you know, it's still the same. This is the estimated slope for BMI for the reference group, right? So when, and again, toggle these if you want, plug in zeros and simplify it, and you'll see this is the slope for the reference group, which is BMI, I'm sorry, which is diabetic no, right? So non-diabetics have this slope. Diabetics would have this slope plus this little difference in slopes, but it's not significantly different, right? So there's really no, there's no significant difference between between the slopes. So just to kind of walk you through this, right? Like where does this stuff come from? Write out the full model. So there's the full model, right? And look at the two different subgroups. So set diabetic equal to 0 first. That makes this go away because 0 times anything is 0. That makes this go away. And so there's the line for non-diabetics, right? Cool. And that's the slope for non-diabetics. Notice it's the same slope as we initially estimated. That's the same one in your output. But what about for diabetics? So just turn diabetic on. So just plug 1 in and 1 in, right? And simplify. So plugging 1 in and 1 in, then we combine like terms. Here's the slope for BMI for non-diabetics plus the estimated difference in slopes. So it looks like diabetics have a bit steeper of a slope for BMI on blood pressure. And remember, it's not significantly different, but it's a bit steeper, right? So the slopes are estimated to be different, even though it's not significant. You can still see that it's estimated to be different. These are the two separate lines for both of those groups. So that difference in slopes there is this slope minus this slope, which is like 0.084, which is what you see right here, right? 0.084. Sorry. And you can actually plot what these lines look like, right? So they're not significantly different. If you plot them, here's what they look like, right? The slope for diabetics is a bit steeper than for non-diabetics. We're allowing the slope of BMI on blood pressure to change for those subgroups, right? So remember mean centering, right? So it's annoying. Like right here, if we look at this output, this is stupid because it's saying when BMI is equal to 0, the difference between diabetics and non-diabetics is this quantity right here, and that's not significant. But no one has a 0 BMI, right? That's such a dumb thing. Like it's not even worth interpreting at all. How do we get around that? So remember from Biostats mean centering, right? This is all totally reviewed. These are literally like my Biostats slides. Mean centering, right? So just take your variable and subtract the mean from it. What you end up with there is that whenever it's equal to 0, that means your original variable is equal to the mean, right? So when you're centered a variable, if you've taken a variable, subtracted the mean, let me just show you. Do I have this in here? Oh, crap. That's annoying. So when you take your, like, let's say you take BMI, you subtract mean BMI from every single value, right? When that new centered variable is equal to 0, that means the original value is equal to the mean. So it's kind of a workaround to make your output interpretable. Now you can interpret, oh, when BMI is average, here's the difference between diabetics and non-diabetics, right? Before, you were interpreting, and it's so stupid, right? You're interpreting like where these two lines are, how far apart are these two lines, way out here where BMI is equal to 0. It's silly. You don't have any data out there. It's stupid, right? It'd be better to look right in here at the mean and say, are these lines significantly different when BMI is equal to the mean? That's all we're doing is tricking the regression into giving us that output. So the mean BMI is 32.91. So we just subtract every single person's BMI, we subtract the mean BMI. Tips for centering myself, go subtract the mean, right? That's all we're doing. So before, there's your data. When you subtract the mean from everything, notice the ones that are really close to 0 now are the ones that before were really close to the mean. If you have a value of BMI that's like equal to the mean, then when you subtract the mean, it's the centered variable is going to be 0. So I typically denote that with an _C just to make sure. All we're doing is subtracting the mean, right? It's just like when you compute a z-score, but you don't divide by the standard deviation. You just subtract the mean. If you don't center BMI, right, you get this bogus thing here. And this is actually, yeah, what does this mean? How do we interpret the intercept, right? Think about that. What does this intercept mean? It's the predicted blood pressure when both of these variables are equal to 0. So when diabetic is equal to 0, that's non-diabetics. Now when BMI is equal to 0, that's silly, right? But that's what this means. The predicted blood pressure for someone who is non-diabetic with a 0 BMI is 50.8. Makes no sense. Instead, let's center, right? So, and I mean, you can interpret these if you want, but it's silly, right? Like, instead, just center it. So take your data, subtract the mean of your data from it, and then just go ahead and run the regression again, same regression, but instead use this centered variable now. And hey, now we got something that makes a lot more sense, right? So for people with average BMI who are non-diabetic, right? So now when this is equal to 0 and this is equal to 0, but when this is equal to 0, what does that mean? When a centered variable is equal to 0, that's when the original variable is equal to the mean. So for those people with average BMI who are non-diabetic, we predict their blood pressure 70.67, right? And notice now we get an estimate that makes a little more sense. So people who are diabetic have a little bit higher predicted blood pressure than people who aren't diabetic when they have an average BMI. So what that's saying is, and I mean, you can interpret these, right? So like take the time to walk through the interpretation. But here's what we're dealing with. If you don't center, you're in this stupid situation right here, where like no one has a mean BMI and you're comparing these two lines. That's your estimate, that negative 1.6 thing. Silly, right? It doesn't make any sense to talk about stuff out here because there's no information out there. Think about that for a homework question towards the end, whether or not you have information to extrapolate to compare between two lines. I ask you to like interpret something, but you won't have data where you're being asked to interpret. When you take the log, you will. Keep that in mind. If you center though, what do you think this yellow line represents? That's just the mean BMI, right? That's just 32 point whatever. If you look at the relationship, the difference between diabetics and non-diabetics, so diabetics is the blue line, right? Non is the red. When you look at the relationship there, you see it's now positive. So diabetics have a slightly higher predicted blood pressure than non-diabetics. And it's not significant, right? It's like still pretty small, but at least it's a meaningful thing to test, right? So take a look at this. This should kind of, I mean, spend some time thinking about what this is illustrating. This is just plotting both of these lines and where you're looking at them. It's the same plot as this one from before, except we're extending it way out here to where BMI is equal to 0, right? Which is silly, but there it is. Cool. So again, right? So I go through a few more examples where, in this case, we're doing an interaction with BMI centered by age category. So now we have three different. We have the reference group, which in this case is middle, right? Because I said it's a middle. And then we have these estimates, and then we have the BMI slope for the reference group. And then we have the slope for young compared to the slope for the reference group, and the slope for older compared to the slope for the reference group, right? None of those slopes are significantly different. So when you compare the slope for BMI on blood pressure for young to middle, it's a little higher for young people, but it's not significant. And it's a little higher for old people. That slope's a little bit steeper, but it's not significant, right? So you can interpret all these things. Cool. So for example, if you want to interpret this, and again, remember, we're using the centered variable now, right? So what does this estimate represent? What does the intercept represent? Think about it. When everything's equal to 0, so when age is 0 and when BMI centered equals 0. So age is 0 when it's the reference group. So the reference group here is middle. So for middle-aged people, and when BMI centered is equal to 0, that's average BMI, right? So middle-aged people with average BMI, this is their predicted blood pressure, right? And you never have to worry about the significance for the intercept, right? It's just testing whether it's different than 0, which is usually a silly thing. You can just ignore those. But what's this testing? So age young, right? So at an average BMI, remember, because there's an interaction here, right? So when BMI is average, it's comparing blood pressure for young people to blood pressure for old people, for middle-aged people, right? The reference group. So young people with an average BMI, 32 point whatever, have blood pressure that's 6 points less than middle-aged people with an average BMI, right? And that is significant. So even after we control for BMI, there's a significant difference between young and middle, right? Controlling for BMI, there's no significant difference between old and middle, right, for people with an average BMI. Here's the slope for middle-aged. Here's the difference in slopes for young. So if you want the slope for young, you can take that plus that. If you want the slope for, right, so like that one plus that one, that's the slope for young. That one plus that one is the slope for older. And you can walk through this, right? So you can interpret these. But it's a good idea to like walk through the full derivation, right? So like intercept, effective old, effective young, BMI centered, old times BMI centered, young times BMI centered, right? So this is the full model. It's pulling out 1, 2, 3, 4, 5, 6 coefficient estimates. 1, 2, 3, 4, 5, 6. That's just where those numbers come from, right? So cool, for old adults, just plug in old 1, turn everything else off. Because if you're old, you're not young, so put in a 1 there, a 0 there, a 1 there, a 0 there. That line simplifies to this, right? So there's the intercept and the slope for older people. Do the same thing for young. So for young, you turn off old and you turn on young. So 0, 1, 0, 1, and simplify that and you get this line. Notice it's a bit steeper, right? Just like we saw. And then for middle age, turn them both off, right? Because if you're not old and you're not young, so 0, 0, 0, 0, turn those off. Combine like terms, it reduces down to this equation, right? And you could switch them around to test whether, you know, old is different from young or whatever. But here are the lines, right? So if you plot these lines, remember the steepest was for young people, right? And it wasn't significant. We can't reject the null hypothesis that these lines have different slopes. But there they are, right? And overall, the slopes are positive. And you could spend time interpreting them if you wanted. But there it is, right? Positive relationship between BMI and blood pressure, but the test of interactions wasn't significant, right? So even though they look a bit different, we can't reject the null hypothesis that these slopes are all the same. I don't think. Nah. What happened there? Oh, I think I accidentally cut off the output here. That's annoying, but it doesn't matter. Cool, because if young people don't differ from old people, I mean, if young people don't differ from middle age, then old are definitely not going to differ from young. So that's fine, because they had a lower mean, weirdly. Cool, and then this thing we saw. So where is it? This significant difference. So young people are significantly lower blood pressure than middle-aged people with an average BMI. So an average BMI is like 32. So you can go to like 32 here, or 33. And this is saying this line is significantly lower than the green line, right? That difference is significant. That's all it's doing, is testing that difference. Cool. And you can get the ANOVA output, right? So whether there's any interaction, this will tell you sort of the overall test. Is there any interaction between age and BMI? And this is saying no, right? So there's no interaction here. That's the same as saying none of these slopes are significantly different. You can get that ANOVA output too. Or you can just do all the individual t-tests and be like, this one's not different, this one's not different, and so on, right? Cool. And then there's like numeric by numeric interactions. I don't ask you about those. It's kind of good to know about. I won't walk through everything, but if you're curious, you may have done one for your project in Biostats. So numeric by numeric, then talking just about assumptions again. So the example I want to show you, you can do the, you know, if you want to do bootstrapped standard errors and stuff, here's just more of that code. Here's bootstrapped residuals. Just a comparison for this example, in case you just want more practice. Here's the example that's good for the homework. And I guess we can talk about it. It's already super late, but in case you're curious about, like, you know, this is a really good example. It maps on nicely to the homework. It's probably the, you had to interpret one of these for your final exam in biostats. Because what we've got here is we've got a categorical predictor, a centered numeric predictor, and then we've got another predictor that's categorical, and it's interacting with the numeric predictor. So we have two categoricals. Only one of them, diabetic status, is involved in the interaction. As you can see, right, there's the estimated slope for non-diabetics. Here's the difference in slopes between diabetics and non-diabetics. So if you do that plus that, you get the slope for diabetics, right? And they're not significantly different. So interactions, sometimes, I mean, they're hard to find, right? There's not lots of, well, I don't know. You can come upon them. You will have a I'm actually not sure. I can't remember. But here's the weird thing, right? The main difference here is just like the example we did before, except for age isn't involved in an interaction, right? Age is not involved in an interaction at all. BMI and diabetic status are, so they're influencing each other, right? They can change, the estimates can change as a function of the other, right? But age isn't. Age is hanging out in the background. So you're just controlling for age. So whenever you interpret this coefficient, right? So let's say you want to interpret this coefficient right here. And I include a bunch of interpretations, right? So all this is saying is, like, I mean, I have them in the slides. Like if you want to see how to interpret all of these suckers, walk through this, right? And I have a bunch of examples. But if you want to interpret this, right? So the effective BMI for the reference group, right? Who's the reference group? Well, the reference group is going to be where everything else is equal to 0, right? So your categoricals. So non-diabetics. And you might be tempted to say young people. And that's not wrong. You can say young people. But since BMI isn't influenced by age, right? Since the two are not involved in an interaction, really what it's fine to say this is the slope for young people who are not diabetic. That's fine. But it's arguably more appropriate to say this is the slope for non-diabetics controlling for age. So regardless of what age someone is, controlling for age, this is the effect of BMI on blood pressure for non-diabetics. Again, we're saying controlling for age because it's not involved in interaction. It's just hanging out in the background. We've accounted for the variability that it can explain. We've taken it out. This is the effect of BMI once we've done that on blood pressure, right, for the non-diabetics. And here's the difference for diabetics, right? So I go through and I give an interpretation for all of these. Take your time with it. Like make this example will really make your life a lot easier for the homework. It's super identical. And then I do another one. Let's see, is this the same example? Glucose, BMI, diabetes. Oh, this is another example where we've just got a numeric hanging out in the background. So glucose, we're predicting blood pressure from glucose, BMI, diabetes, but glucose isn't involved in the interaction. Diabetes is, right? And so I walk through and talk about how to interpret those two. So that's it. Take your time though, like walk through those, especially if this is rusty. God, sorry, yeah, I appreciate you. I mean, this is all just review stuff, so don't sweat it, but I wanna make sure that like, you can review this if you want, because I don't want you to have to go and dig through your old biostats slides. So I just wanted to kind of copy these over to make sure you have them. Cool. How are we doing? This has been a lot of me. Yeah, most people pieced out. That's fine. Any questions about this stuff? I know it's kind of a lot, but it's kind of review too, right? So hopefully this is kind of ringing faint bells and like, oh yeah. Yeah. How are we doing? How do I do maybe I can stop sharing. Oh, my video is actually working today, which is super cool. Let me stop.